Welcome to our solar system. Coming up soon, you're going to be doing a satellite investigation so you can explore one object of our solar system in greater detail. We're going to start out here with just an overview and then a look at the terrestrial planets. So what does our solar system include? Well, it includes one star, the Sun. It includes 8 planets and their satellites, or what we might call their moons, asteroids, comets, meteoroids. We'll eventually talk about what the difference is between each of those, and dwarf planets. Here's a cartoon of our solar system, and you can see the Sun is in the center. The terrestrial planets, which we'll talk about in this video, are located closest to the Sun. Then we have the asteroid belt. Then we have the Jovian planets. And then a belt of objects that we've only discovered probably in your lifetime, if you're only 20-something, is known as the Kuiper belt. And that word Kuiper rhymes with viper. And these are a bunch of icy objects very, very far in our solar system from where we are. And Pluto is now a member of the Kuiper belt. Remember that all of the planet orbits are roughly in a plane, similar to a flat sheet of paper, and the Earth's orbital plane is called the ecliptic. The formation of the solar system was discussed in earlier learning videos. The nebular hypothesis, or sometimes the nebular theory, is the name we give to the formation of stars. Stars and their solar systems form from nebula, such as the one shown here, and our solar system began to form about 5 billion years ago from a nebula. What are the planets made of in our solar system? We have quite a few planets that are made of hydrogen and helium. We have the rocky planets made of silicate minerals and metallic iron. Earth is one of those. And then we have planets that are pretty far from the Sun, where it's very cold, that are made of ices. And if you look at this list, you might think, well, these are gases, not ices. Carbon dioxide, that's a gas. But if it's cold enough, it freezes. Just like water can be a gas, a liquid, or a solid on Earth, the colder it gets. Here's a slide that we're going to return to as we discuss terrestrial planets in this video and Jovian planets in the next video. Which objects in our solar system have liquid water? Well, Earth, for sure. And then there's going to be one more promising candidate. Why is this of interest? Generally, we believe that for life to exist, it needs water. So having liquid water is important if we want to see if there's life anywhere else in the solar system. It's also important if we ever think about colonizing another place. We need water. What about volcanically active? Well, we can put the Earth there as well. And that's of interest because our atmosphere formed initially from volcanic activity. And so we're interested in other objects in the solar system that have volcanic activity occurring. So as we come across these objects, we'll come back and add them to this list. So the two groups of planets that I pointed out earlier are the terrestrial or Earth-like planets that are closest to the Sun. That includes Mercury, Venus, Earth, and Mars. You don't have to memorize the order of the planets or a lot of the information I'm going to talk about because it's on that planetary data table that you saw in lab. So some of this is just information that you don't really need to write down. However, I do want you to make sure you understand the unique features of the terrestrial versus the Jovian planets. So the terrestrial planets are small in their size and their mass. They're high density. They're compact because they're rocky. On the other hand, the Jovian or Jupiter-like planets are large, have enormous mass, but have low density because they're so huge, and they're mostly made of gases. So there's a big difference between these two groups of planets. This picture shows the planets next to each other drawn to scale. You can see the 4 terrestrial planets are itty-bitty tiny compared to the gas giants, right? Also, these look like surfaces on these gas giants, but these are all clouds. You can't land on Jupiter or Saturn because you would just go right through the clouds. Also in this picture is the Sun for scale. The inside of the planets are estimated here. We know a lot about Earth's inside, but the other planets we have to guess. In general, though, we believe the terrestrial planets have some sort of metallic core, and they've included the moon here, and then a rocky crust and mantle. The Jovian planets, on the other hand, have on their outer parts visible clouds, and then gaseous hydrogen, and then maybe ices maybe a rocky core, and Jupiter and Saturn are so massive that there's actually some really unusual phase changes that occur that turn the gaseous hydrogen to liquid and then metallic hydrogen. Again, this is somewhat theoretical because we can't go down there and study it. Why not? Because the gravitational pull is so great on these massive objects, it would crush any instrument we sent down there. A quick tour on the terrestrial planets. Mercury is the innermost planet, it's the smallest, and it has no atmosphere. This is a picture of it. It looks kind of like the moon. Because Mercury is so close to the sun, it has the greatest temperature change of anywhere in the solar system. The daytime side that faces the sun gets as hot as 800 degrees Fahrenheit, or 430 degrees centigrade. The nighttime side gets as cold as minus 290 degrees Fahrenheit, or minus 180 degrees centigrade. So not looking like a very good place to go hang out if we wanted to go to some other planet. This is a time-lapse photo of Mercury during the year 2000 in March. And if you look very carefully, you can see points here. So these were taken night after night after night and then put upon one background. One interesting thing about Mercury is you're only going to see it in the sky during dusk or dawn. And that's because of the position of Mercury relative to us. So here we have the sun. Mercury goes around the sun and the Earth goes around both of those things at a farther distance. In the position I've shown it here, for Earth, this side of this line is the nighttime side of Earth, right? If you're on Earth and you're looking out in this direction, it's dark. If you're looking out in this direction, it's daytime. And so remember, Earth spins on an axis. So the only time you're going to see Mercury, no matter where it is on this orbit, is just when the sun is coming up or just when the sun is setting. Of course, it's us that's moving. And the same is true of Venus. Speaking of Venus, second to the moon in brilliance, very, very bright. If you look in the sky during sunset, you will see a very bright star, and that will not be a star, it'll be Venus. It's similar to Earth in its size and density and location in the solar system, but other than that, it's very, very different. Venus's surface temperature averages a balmy 900 degrees Fahrenheit. It's shrouded with clouds, so we can't actually visibly look down on a surface, and we've been able to map it with radar. The atmosphere is 97% carbon dioxide. Our atmosphere is a fraction of a percent of carbon dioxide. So Venus essentially has the greenhouse effect, extreme greenhouse effect. Sunlight goes in, it doesn't go out, it gets very hot. And as a result, the surface pressure is about 90 times that of Earth. So probes have been sent to the surface of Venus, they go down to the surface, and they get crushed and they melt. Not a good place to move to. So as I said, scientists were able to map Venus's surface with radar, and we found that mostly there were extinct volcano flows on the surface of Venus. Here's a computer-generated map of all of those radar images, and the colors indicate elevation. Really, radar comes out like this, like black and white. And what you can see here is there's a ridge that seems to be broken, and the geologists have interpreted as a lava flow, an ancient lava flow, that broke through, moved from left to right, and filled these areas that are bright white here, which were large lava flows. Again, these are extinct volcanoes. Every once in a while, Venus passes in front of the sun, and that's called a transit. And Venus transits twice, 8 years apart, every 110 years or so. The last time there was a transit pair, it was in 2004 and 2012. I was outside at PCC with my solar compasses in 2012, trying to get people to look at the transit, saying, it won't happen again for over 100 years, you got to check it out. And some people watched, some people thought I was crazy. In any case, here's some pictures of it, and it's just showing when those transits occurred. So this was figured out quite a while ago, and in fact, Halley, the famous Halley comet guy, realized, and by the way, the reason he was known for that comet is he predicted the return of that comet in 1682. In any case, he knew about these transits, and he thought we could measure the Earth-Sun distance, an AU, if we were able to put people around the Earth and time when Venus passed in front of the sun and then to leave the sun, and we could use parallax to determine that angle. Unfortunately, Halley died in 1742 at the age of 85, so he wasn't able to see this result. But many British and French expeditions did occur, and we're going to pick up at the next video so you can hear the tragic story of French expedition leader Guillaume Joseph Hyacinthe Jean-Baptiste Le Gentil de la Glacier.